Hey, what's up, guys? Yeah, so in this video, I would introduce the algebraic closure, and I think this is also a very important idea in the algebra and the field theory. Okay, so let me start explain. Okay, I think everyone knows about what algebraic closure means. At least if you remember like high school, right? So the simple example. So basically, the idea is that okay, maybe let me just give a definition. So let me just introduce what algebraic close. Okay, so algebraically close. Okay, so when I say a field is algebraic close, if every polynomial of the coefficient f have the roots. So I should say every non-zero polynomial of x belongs to f of x has all its roots in f. Okay, so probably the only example that you know is that complex number. Right? So you know that from your high school or like the complex analysis, and or you can use the Lugano theorem, or if you know more about the fundamental group of circle, then you can also prove this. Okay, but probably this is the only one that you know which has this property. Okay, but mathematically, which is very interesting, that actually any field has its algebraic closure. Okay, so let me just explain. So when I say, let me just give definition. So let's say K bar, I use K bar is algebraic closure of K. So somebody give you a field that's K. So K bar is algebraic closure of K. Okay, so satisfy the first one is that if K bar is algebraic over K, so every element in every polynomial in K bar of X has solution, has the polynomial equation which has its own roots in K. And the second is that K bar is algebraically closed. Algebraically closed. Okay, so this is the algebraic closure. Okay, so theorem. This is very non-trivial if you think about it as a set theoretical question. So given any field, K, one can has its own algebraic closure. Algebraic closure. K bar. So basically, I should say K bar is always exist. So sometimes in the Galois theory, that you can just present it as a, because in the Galois theory usually you were only working on the rational numbers. So the complex, so you know the complex number is algebraic closure. So usually, if you not study the numbers theory or something which is very abstract, that's probably you don't care about this theorem, because in a lot of cases that I think the K bar description is not very clear if your K is really weird. Okay, but as a theoretical question, this problem is very interesting. Okay, so maybe in the next video, then I will discuss the algebraic closure of finite field. Okay, so this is so for example, I know that algebraic closure of the real number will be a complex number. And so how about algebraic closure of finite field? For some P, this is really weird. Okay, so this is another thing that you need to explain. Also this is a famous algebraic closure of the rational numbers. It's called algebraic numbers. So this is called algebraic number. Okay, and there is a famous thing called absolute Galois group of this Q bar over Q, and this group is very, I think up to now, modern mathematics still investigate the property of this absolute Galois group. Okay, so let's dive in the proof. So the proof has three different way. The only the final the third way I want to explain is 100% rigorous. So let me just present the informal way. So the first one is informal. So one informal way is very weird that since I know, so since remember in the previously that we already proved that so if you have a f of x, right, inside k of x, if f of x has degree greater than 2 and irreducible, so it means f of x has some roots which is not in k, then basically you can do the quotient, right? So basically you can put your k of x k into this quotient ring, and in this k of x f of x, this f of x will have roots, right? You can check that if you send x to, let's say, x plus f of x, sorry, a plus f of x, then you can check this is 0. Okay, so basically you always get the roots by keep adjoint this, right? So the idea is that you can start from k, and informally maybe you put into the k1, which k1 is a field such that every non-zero polynomial of k has roots, and you can get k2, and you can get k3, and obviously that you can define k bar to be union of kn from n from, let's say, 0 to infinity. This is k0, and obviously that if you take any polynomial f belongs to k bar of x, then there will be this n such that this f belongs to kn of x. But every solution in kn of x is already, all the roots of kn of x will belongs to kn plus 1. Okay, so which prove that the k bar is algebraic closed, and also you can prove that obviously that k bar is the algebraic extension of k. Okay, because all these extension are algebraic, and the composition of the algebraic extension will be algebraic. So this is the informal way. The reason is that this construction do not give you the clear description of K1, right? Because it seems like you may need to do the uncountable or countable, probably uncountable at the joint to get your K1. So there will be some set theoretical issue. Okay, so the reason is that there will be some set theoretical issue to construct this K1. Okay, so this is the problem. Okay, and the second way, basically, I think it's also a bit strange. This is proposed by our team. And this way is also, you can define omega, let's say, which is all the field F, which is K is as a subfield, and F is algebraic over K. Okay, and you can define a partially order because let's say you can define partial order such that f1, if f1 is a f2, if you have this, then I can say that f1 greater than or equal to f2. Okay, and omega has maximum element. The reason is that you can do all the union of f, right? So you can do all union of f, which will be maximum element. Sorry, I should say has an upper bound. Okay, so by Zhong's lemma, there will be the maximum elements, right? Because you get right, so there will be a maximum elements. And this is k bar. Okay, the reason is that if k bar is not algebraic closed, then you can get another field, right, which is larger than k bar, right, which is but not same as it. You get some polynomial and your quotient, you get something larger than k bar, it's a k bar prime, but this violates the maximality of k bar. Okay, and by definition, k bar is algebra over k. Okay, so it seems like we get a proof. Okay. Okay, but this proof also not 100% rigorous. Okay, the reason is that this omega is not a set. Okay, so omega is not a set. It's not a set. Okay, because I mean you can check this, right? Because this proof do not use this algebra over k. Actually, I mean you can delete this. and view K as a set, and F is a set which include, then you will prove that there should be a largest set which contains the set K, which is nonsense. Right, so this proves the problem is that omega is not set. So this proof is also not 100% rigorous. Okay, so if you go to the textbook, then you can see the 100% rigorous proof, which is very, very tricky and probably nobody cares. But I still want to do the video. Okay. So let me just explain the proof. Okay, this proof is very tricky. Yeah, so how to understand? Okay. So the idea is that you start to take K R to K, and you take every, okay, so maybe let's do this. So you take every non-zero point, the degree greater or equal to 2 polynomial, let's call it F, right? So all of the polynomial belongs to K of X, forms a set, right? So let's call this, maybe let's call it I, and I belongs to some set I. So this F of I can be uncountable and then maybe countable. Okay. So your K, and then for each Fi, you give each of Fi has a variable. Let's call it Xfi. So I use Xfi to denote the variable corresponding to F of I. Okay. And then you add join all of these F of I. Okay. And you call it R. Okay, so notice that this construction, although there's infinite of them, right? But once I write any, for every time I write any element in this set, I assume that there is a finite sum. Okay, so which makes this R well defined. Okay. And now you can create an ideal, right? Let's say you have ideal that's generated by Fi x Fi. Okay, so this looks like a Cantor standardization, right? So you can take ideal which is generated by each variable and put into F of I of X. Okay, and this is the ideal of R, right? Because this is an element in R and I put generated. Okay, so theorem, which is I is proper, means that I is not the same as the whole ring. Okay. So let's quickly give the proof. Okay, so proof is proved by contradiction. So suppose there's some coefficient, let's say gi fi of x fi, which is 1, right? Because suppose this is generated by all ring, right? If only if generate the identity. Okay, so if this is true, and so this gi is a coefficient in gi is some polynomial in it, right? So each G1 will only contains each GI will only contains the finite of variables. So there are only finite variables. That GI involved. I should say these very finite variables get involved in the GI. Okay. So let's call it x1, x2 up to xn. Let's say this is the which you have n of lip, right? This involved, and I get xn1, xn2, xn. Okay. So these are the rest. Okay. So I can create another extension field E, which you put all these field in it. So x1, x2, x3, xn, and xn plus 1, xm, quotient some identity. Quotient some relation. So I can smartly choose these guy to be 0, right? So basically I can choose f1, x1, right? So they're a variable, right? So I can make this f1, xf1 to be x1, right? So I choose fi to xi. Okay, so this is f1 of x1, f2 of x2, fn of xn. I make it 0. Okay. Okay, so you can easily say that see that E is a finite algebraic extension. So I should say that E is in E. It's E in E, right? In E, this relation cannot hold, right? True, right? Right? Because in E, all of these guys 0, right? So, and then this is 0 equals to 1, right? So no, not. So nonsense. Okay, it's contradiction. And you can see that you can put k into this, right? So that means if you find extension of k which satisfies this property, and this relationship will violate the results, will violate this construction. Okay, so contradiction. So I is proper, right? Okay, so now we need the famous result of Zone's lemma. You can go to my ring theory. So there is a ring theory result that if you get given any ideal, there's a maximum ideal containing any ideal, right? So there is this a maximum ideal. Okay, so this is maximum ideal. Okay, this is proved by Zone's lemma for any commutative ring with identity. Okay, so now you can create a field, right? Because you have a maximum ideal and a ring. So the simple ideal is that you can construct R over M, which is a field, right? So actually this is K bar. Okay, so claim R over N is algebraically, I should say R over M, sorry, not K bar. It's called K1. So R over M, which is K1. So the fact that every non-zero polynomial in K of X has its roots in K1. Okay, so this is what I meant to prove. Okay, so proof it's almost trivial, right, by construction. Right. The reason is that I mean K defined to be is K1 defined to be the original R defined by M, right? So at least you can put K in here, right? So if you put any K, right, let's say you can do the map, right? So let's say you try to map this Fk to K1. You can map, let's say let's say you have X. Let's say you have variable maybe xf, and sorry. So let's do this, right? So let's see. So this K1 is defined to be R quotient M, right? And the M is covers this I, right? So which means that I mean one easy map that you can construct is that you start from R and map to R divided by M, right? So let's say you have variable xf, and once you define each xf, then you will create, right? So let's say you have xf plus m. Okay, so there's a relationship in this, right? So basically xf plus m, right? But this m is larger than all sf generated by xf, right? So it's 0. Okay, so that means that each basically this prove this. Okay, because or basically you can think that because up to from this way, then every polynomial that this every fxf, right, is basically 0 by enforce, right? So, but basically use this set construction, and I bypass the set theoretical issue, and I can get this. So basically this follows that every non-zero polynomial in K of X has its own roots in K1 by just using this equation. Okay. Okay, so now I get a tower. I get tower. So for now, which every non-zero polynomial of K has its roots in K1 and also tower K2, K3. Okay, so fact, and this is the inclusion. Okay, this is some map. Okay, which is injective. Okay, so you can take K bar to be the union of Kn and from 0 to infinity, and the reason is that just the same. If you take F belongs to K bar of X, and you can take the whatever, right? You can take there exists n such that belongs to Kn of X, and all the roots in K of F will belongs to Kn plus 1, right? Which belongs to K. So that means K bar, right? So each roots in the K bar. So K bar is algebraic closed. And then one might worry that this map is not injective, right? Because it's injective but not inclusion, right? So basically, there's maybe multiple ways to do this. Okay, so if you are very technical, then you can say that this is the colimit, right? But basically, you can take colimit of its k, and but you get the results the same, which k bar is algebraically closed. And don't worry that I will post a reference below so you can check it. Okay, and there is a fact that I want to say that the fact there's some fact that there's some fact that I want to say. Fact one, which is I think it's very simple, so I should quickly give the proof. Okay, so this fact is that so the following are equivalent. Okay, the first one is that okay, so the only algebraic. The first statement is that the only algebraic extension of k is k itself. Okay, so that means you can view k as an algebraic close and algebraic closure. Okay, and then so basically in k of x, then every irreducible polynomial has degree 1. Okay, and the third fact is that every non-constant polynomial in k of x has a root in k. Okay, these are three are the same statement, and proof is trivial. Okay, you can try to prove by yourself. Let me just quickly prove. Right, properly. Okay, so let's compute. Let's say 1 implies 2. Okay, the reason is that let's say the only algebraic extension of k is k itself. So in k of x, every irreducible polynomial has degree 1. Right, so let's say you take k cube belongs to k of x, which is irreducible. Then your e k of x quotient q has degree, right? This is why I just proved, why originally proved has degree q, right? But you know what? The only algebraic extension is itself, right? So it must be 1. Trivial. Okay. Okay, let's say 2 implies 3. So 2 is what? In k of x, every irreducible polynomial has degree 1. And then we'll prove that every constant has root, right? This is trivial, right? Because every irreducible, if otherwise that there is no constant, if this, so 2 must imply 3 because every irreducible polynomial has degree 1, right? So every non-constant polynomial must have roots. Otherwise that irreducible polynomial cannot be degree 1. Okay, so this is also trivial. Okay, how about 3 implies 1? So 3 says that every non-constant polynomial in k of x has a root in k. Right, so basically, right, so if you have non-constant polynomial, it must have roots in k. Okay, so it will keep factorized, right? Otherwise, right, so suppose that alpha is algebraic, let's say alpha is algebraic over k, right? And then you can take the irreducible polynomial, minimum polynomial alpha k has a roots, right? Has a roots r in k, right? By the third fact, so that what? So the q must be x minus r, right? And the q of alpha is 0, so alpha equals to r, right? So this is just the proof. So alpha is algebraic in k. Suppose right, alpha you get some alpha extension, so you get algebraic extension alpha, and then pick one which is roots in k, right? So that's and the irreducible, so q must x minus r, and the q of alpha is 0, which give you alpha equals to r. Okay. Okay, so there's a fact and then a theorem that I will not prove here because I prove is very tedious, right? But I will give you the reference. Okay, so actually you can prove by Zhong's lemma. Algebraic closed field, the algebraic closure. I should say algebraically closure. I should say algebraic closure. Sorry, algebraic closure of K is unique up to isomorphism. Okay, so this means that theoretically speaking, any algebraic closure of the any field is unique up to isomorphism. Okay, so that's it. And the next video, then I will describe the finite. Okay, so next video, I will give you the results about the finite. I should say the algebraic closure of finite fields. And this is very interesting topic that I think very interesting. Okay, so see you guys next videos.